Hyperscale elastic pools have been generally available for some time now, but there are some really amazing things that you might want to know and that you might learn in this episode. Learn all about it this week on Data Exposed. Hi, I'm Anna Hoffman, and welcome to this episode of Data Exposed. Today, I'm joined by Arvind from the SQL Product Group. No stranger to Data Exposed, but Arvind, can you tell us a little bit about what you do?
Sure. Thanks, Anna, for the opportunity again to be on the show. I am Arvind, as Anna just said. I am a principal product manager in the Azure SQL database team. My focus is on this awesome piece of technology, Hyperscale, and I try to deliver value in terms of cost optimizations through the feature called Hyperscale Elastic Pool. It's been 6 months almost since we announced general availability, so I'm really happy to be here, talk about it from a practical lessons learned and insights perspective.
Awesome. And this is a jam-packed session, folks. You're not going to want to miss a second of it. Arvind's going to walk us through 5 key insights and really some key things you need to know. And I think you're going to walk away very happy about some of the things you're going to learn. So with that being said, let's get right into it. Arvind, to kick us off, I have one question for you. And maybe some folks are familiar with elastic pools, but what's hyperscale elastic pools and how does this work behind the covers?
Sounds great. So Hyperscale Elastic Pools is one of the techniques we have. It's a technology and an offering in Azure SQL, which allows you to optimize price and performance across a group of databases. And the primary means that we use to do that is by using this team of shared resources. What does it mean? In the end of the day, if you compare it with a real life analogy, like a carpool, for example, you kind of get it. Let's look at it a little bit deeper, though, from the perspective of SQL and how resource pooling or shared resources works in hyperscale elastic pools. So, just as a recap, some of you might have seen the previous episode where I did mention the fact that with individual databases, so if you actually look at this picture here, we have 8 databases, each with individually unpredictable resource requirements. In this case, you have to do a lot of work to try to optimize the sizing in terms of resource allocated to each of these databases. What we can then do by pooling them together is potentially transform those individually unpredictable workloads to a collectively stable and more predictable workload pattern. So, pooling resources allows us to economize the amount of resources allocated because we are smoothing things out by grouping these databases together. So it not only eases sizing, but as you can think about, it may also, in many cases, save you costs because you're pulling things together. Let's take a little bit of a deeper dive into what exactly is pooled, what is shared, and therefore we'll actually see some demos in terms of the proof or the pudding, as I call it, seeing how this resource pooling works. So the main thing that's shared, which is kind of obvious, is the CPU resources. So these are allocated at the pool level. So whether you have just one database in the pool or you have 25 databases in the pool, the total number of resources at the pool level is constant. It's what you allocate. It's what you configure. Memory as well is therefore shared. Also, local SSD cache, which is one of the unique features with Hyperscale. We have this awesome local SSD cache. We call it RBPEX, which is Resilient Buffer Pool Extension. That's shared across all the databases in the pool. The number of worker threads and hence the number of requests you can run in parallel are shared, and things like external endpoint invocations. So let's say you're calling into OpenAI from within Azure SQL, that is shared as well. Let's take a look at this in action. I have a pool which is called Hyperscale Pool 1. And as you can see, we have multiple databases which are in the same pool. This query uses a sys.database service objectives DMV to actually list all these databases. These databases, because they're in a pool, their service objective is actually called Elastic Pool. I can view the amount of resources allocated to each of those for the pool itself by using related views like sysdm OS performance counters and sysdm OS sysinfo. I'm running these queries from within the tenant DB01, And as you can see, it spits out the start time for the process, the SQL Server.exe process that was associated with this pool. Please keep a close eye on this. It started at 3 minutes past midnight, 3 hours, 25 minutes past midnight. And keep an eye on this instance name. This is actually the named instance that is associated with the Elastic Pool running behind the scenes inside Azure SQL database. Again, as a reminder, this was from the tenant DB01 database. Let's see how things look when we switch context to tenant DB02 and rerun this. You'll see the same start time, kind of hinting that it's the same process, and then the same instance name. I'm going to do this real quick back and forth. So you'll see that nothing changes other than the database name. So this is kind of the proof of the pudding that behind the scenes for every Elastic pool, there is a shared process, a single SQL Server.exe, which hosts all these databases. And this is kind of the proof of the pudding for you, like saying this is how Elastic pools work under the covers.
Awesome. Cool. That's super interesting. I just learned like 6 things. So this has already been awesome. Okay. So one of my questions, and I think you're going to get into this, is like with some of the resource sharing that you just explained, like some immediate concerns come up around like security and isolation. Like how does that work?
Wonderful. And just like if you're living in a shared, homestead, for example, you're always wondering about privacy and isolation. The great news is with hyperscale elastic pools, and in fact, even in the other types of elastic pools like general purpose, the key thing that led to our implementation was this strong focus on isolation. You'll see it in multiple ways. The first thing I'm going to focus on is the accessibility or lack thereof of databases. So they are strongly isolated. The best way to see this in action is to actually run a simple demo. I have the same setup, 8 databases in the single Elastic pool. I'm running this query from tenant DB01. Um, to make things easier to showcase here, I ran this really expensive query, which is going to probably take like years or decades to complete, just so that we can showcase the behind the scenes action here. So we have requests, sessions, these are usual DMVs. And when we run it from DB01, you could see the query that was running. But when we switch to DB02, you can see that the query is no longer visible from the other database context. I went through that real quick. So I just want to emphasize that any database in an Elastic pool, if it's running a query, even from management views like sysdm exec requests, sysdm exec sessions, and so on, there is clean isolation. The other database has no knowledge about the workloads that are running in the other databases in the same pool. The same thing applies even to three-part naming conventions. You may think that, hey, because these are all in the same instance, the same pool, can I start referencing objects across databases? And with Elastic Pools, we make sure we can't do that. And this is a by design thing. It's not a bug. We want to ensure strong isolation. You'll see the proof here. So we have tenant DB01. We're running the query within tenant DB01. So it's kind of okay to use the three-part naming. But the minute I start hopping across databases, I am cleanly blocked with an error saying, hey, you can't do this in this version of SQL, which is Azure SQL Database. Strong isolation, no compromises at any point in time.
Awesome. That's great. I'm sure that gives folks a lot of reassurance. I mean, kind of related to this comes to the resource sharing when it comes to noisy neighbors, right? Because
Oh,
if
yeah.
you are sharing and cost optimizing, like, is one going to influence the other's workload if it's really busy?
Right, right. And this is a distinct possibility. But the good news is, again, we got some things up our sleeve which will help you in this regard. I want to take you through this in some detail because this is core to how you can effectively resource govern and have some control over these competing workloads in a shared resource model like Elastic Pools. To do that, I'm going to introduce the concept of limits. These are not bad limits, they're just the capabilities that we publish. There are two levels of limits that you should know about, and you may already know about. The first level of limits is at the pool level. The pool is, as we saw, an instance of SQL, and it comes with certain limits or capabilities that we publish. The first thing you should know about is the maximum storage per pool. Each database has its own allocated storage, but the sum total of that cannot exceed 100 terabytes or TB bytes to be precise per elastic pool. Logging, so when you're ingesting a lot of data into the database, cannot exceed 100 MB bytes at the database level. But this is one of the cool things. With pools, we give you certain value added features extra. At the pool level, you can still exceed the 100 megabytes per database. So that still remains a per database limit. But when you have lots of activity across each database, so the sum total of them can still go to up to 125 megabytes. So this is a very important thing because sometimes people compare and contrast what's inside a single database versus what's inside a pool. Pools, you're allowed to do certain things above and beyond what you would do with a singular database out there. And just be aware that this limit is going to go up even more publicly in the near future. We already have a limited preview for increased transaction log ingestion rates or generation rates. Take a look at this blog post, which covers some of the improvements in that area. And last but not the least, the number of databases per pool is capped at 25 TB. So this was the pool level limits. All of these limits are documented in our excellent documentation. We have them at a short URL here. HSEP is HS Hyperscale Elastic Pools, and then there's a sub URL for limits. The key things you want to watch out for: how many megabytes of RAM, how many databases per pool, how much storage per pool, and then this transaction logging thing that we just talked about. Um, to take that further to the noisy neighbor problem. So we got these pool level capabilities. How can you ensure limits so that each database cannot run away with that whole pool's worth of resources? The best way to do that is to use a configuration option which is applied at the pool level, which allows us to set a per database maximum. So I'm going to take you through this real quick in this simple demo. We use the configure option within the elastic pool. And then, as you can see here, this is a hyperscale elastic pool. It has 24 vCores and it has one secondary replica. It has multiple databases in it. This is the same pool that we saw in the previous demos, and they have some activity on the databases. We use this setting, which is the per database setting. I'm going to use that either to set the max, which is this slider right here. You can set it all the way to the number of vCores at the pool level. You can also set a minimum. The minimum, interestingly enough, and if you think about it, it's actually very logical, cannot exceed a threshold which would otherwise cause it to be exceeding the number of vCores in the pool. So just to make this real interesting, we have 8 databases in the pool. I'm attempting to set a minimum allocation of 4 vCores per database. That will never be feasible because 8 times 4 is 32 vCores, and we only have 24 vCores in the pool. So be aware that setting a minimum which is too high is not possible depending on the number of databases. And also the maximum here, that's the crucial thing. In most cases, customers just set a maximum and they leave the minimum at 0, and they'll set the maximum to, let's say, 4 vCores or 6 vCores or something tangible, something concrete, so that no single database can spike the resources in the pool and exhaust available resources. I'm going to keep going into a little bit more detail here. Um, the the per database setting not only controls the amount of vCores, it also proportionally controls how many IOPS you get on that local SSD cache. It controls how many worker threads you are allowed to use and the amount of external endpoint conversations or invocations that you can have concurrently. The other neat thing, and this is again by design, it's not a bug, is the fact that even if you set a per database limit at the pool level, the transaction log throughput is a constant 100 megabytes per second. This is by design, and it's one of the unique things with Hyperscale where, regardless of how many vCores your database has, even though it's in a pool, it's going to be a headroom of up to 100 megabytes per second for transaction logging. To take a quick look at this using a magic PMV, I think this is one of those hidden gems not many people know about. It's called SysDM User DB Resource Governance. Highly recommended to take a look at this DMV. We're going to look at it in our demo here. What this does is it helps you visualize the effect that those sliders have, the min, the max, especially the max, how does that reflect on your per database throughput? How, let's take a look at that in this simple demo. So we have the same pool. We're going to work with that for simplicity. I've scaled this pool down a little bit. It's gone to 20 vCores. And we're going to change the per database value, which is currently at 20. We'll change it later. Let's take a quick look at how the maximum of 20 reflects when it comes to this DMV called sys DM user DB resource governance. This huge string that's here is actually the internal representation. It actually shows you that this pool has a min 0 and a max 20 associated from a database level cap or a database level limit perspective. You can also see things like the amount of SSD IOPS, the amount of transaction logging throughput, the amount of vCores, and so on. All these magic numbers are actually all documented as well, but you can view them in the context of this DMV. So we're going to take a quick look at docs and see if these reconcile. So just remember the magic numbers: 80,000, 2,000 for the number of worker threads, and 150 for the number of outbound external endpoint invocations. And voila, if you look at our documentation, this is a short URL to get to the per database limits for Hyperscale. You'll see that the database because we set the per database max to 20, you get 80,100 megabytes per second, 2,000 worker threads, and 150 external endpoint invocations. So I'm just trying to reconcile what we see in the DMV with what is documented, just so that you kind of see that we are very, very transparent about all these limits. What if we change the value, though, to, let's say, 4 vCores? So you can see that we'll dial that back down to 4, hit save, and then we'll take a look at the DMV again, just to see how things reconcile. And when we do that, we expect to see from documentation, we expect to see 16,000 local IOPS, 100 megabytes per second, still constant, again, because this is the constant transaction logging that we talked about, 400 worker threads, and 40 external endpoint invocations. And again, very simple system user DB resource governance. We see the proof of the experiment there: 4 vCores maximum for this database, 16,000 IOPS, constant 100 Mbps logging, 400 worker threads, and 40 external endpoint invocations. So I would just want to summarize this demo by saying that, hey, if you're working deeply with Elastic pools, even single databases for that matter, do be aware of this magic DMV. It's got a whole bunch of information in there. Um, Great resource for experienced administrators to look at.
Nice. Awesome. This is great to see. Okay, so I think this leads to one of the last items, and that's around how fast does this thing actually scale?
Yep. Hyperscale, and I just want to stand a minute here. The name hyperscale sometimes tells people that, or kind of implicitly says, "Oh, this is only for the big, huge databases," and it's not always the case. You can start with a database which is as small as 10 gigabytes, but the scale in hyperscale, I personally feel it is to do with the scaling. So you can go up and down, you can scale up and down, and you can scale in and out. To add read-only replicas to your hyperscale Elastic pool. I want to show you 2 compelling demos that I hope will drive home the point. The first one is centered around vertical scalability. To do this, we are going to use a pool that's a slightly different pool from what I've shown you so far. It has 4 databases in it, but the awesome fact is these are maxed out. We're close to the 100 TB bytes max for the pool, 97 to be precise. And this pool has just 6 vCores. That's unbelievable, right? You can have this huge, kind of asymmetry between the data and the compute. Now, it's possible because of the hyperscale architecture. We have a compute layer that is completely different from the storage layer. So when we scale things up or down, like from 6 vCores to, let's say, 24 vCores, we just scale the compute layer, and the storage layer behind the scenes remains unaffected. This is a modern cloud native architecture which allows us to scale this kind of a huge pool in like 3 minutes, which is amazing. If you wanted to do this with conventional technology, you
Wow.
would be moving, yeah, we would be moving all that data around in conventional technology. With this cloud native architecture that Hyperscale enables, no data movement, only the compute scales. 3 minutes is typical. Your results may vary, of course, but this is kind of in the ballpark of where we expect production scaling operations to be. And it's the same whether you add replicas as well. Like we just saw a vertical scaling operation. If you add replicas or scale down the pool, or sorry, scale the pool inwards, if you may, by removing replicas. Like in this case, I'm going to add a replica. I went from 0 to 1 replica, and the replica allows us to do things like high availability. We can have read-only workloads using that replica and so on. But again, scaling this from 0 to 1 HA replica, again, I'm fast forwarding a little bit for the interest of time. You will see this. This is no coincidence. It's around the same 3 minute mark. It's almost always predictable and constant time, regardless of the amount of data you have in the pool. So again, just to reinforce some of the advantages of the hyperscale cloud native architecture, predictable and quick scaling.
Awesome. I love it. And we have just about a minute left. But Arvind, I know people want to know about cost. So can you tell us like how this looks from a cost viewpoint?
Very, very good question. And this is something which is on the top of everyone's mind, or should be, especially given the focus on economic and kind of financial efficiencies today, right? So when it comes to billing hyperscale elastic pools, I want to just recap some of the key things that are involved. The compute associated with the elastic pool is charged. It's charged on a per week or per hour basis. In the case of hyperscale elastic pool, we add on a specific cost element. This is for us to reflect the value that we're delivering through hyperscale elastic pools. You noticed we have things like higher log limits at the pool level, the huge cost optimizations that you can potentially get by pooling together these databases. So this is an additional cost which you'll only see associated with hyperscale elastic pools. And that's again a per week or per hour cost. Both of these are constant at the pool level. So if you size a pool for 20 vCores, this is going to be charged regardless of whether you have databases in the pool, whether there's activity in the pool, and so on. The other element of cost that you should be aware of is the data and the backup storage costs. These are per database. They are dependent on the number of databases that you have in the pool and how big they get. So the sum total of your costs will be the costs associated with the pool and the costs associated with each database in the pool. And I just wanted to compare and contrast. This is by using just publicly published prices. And this is an estimate. I took an estimate of a general purpose elastic pools with 18 vCores allocated to it, compared it with the cost of a 18 vCore hyperscale elastic pool provisioned with the so-called standard series hardware. This is our so-called Gen 5, or the standard series hardware that we have available. And then to top it off, I looked at the premium series hardware. This is the latest generation hardware that we have. The principle in hyperscale is because you can right size your compute and your storage independent of each other, and you can leverage newer hardware like these PRMS or premium series hardware. Let's say theoretically, this particular workload, you could optimize it to use lesser vCores. So if you look at the bottom line, let's say GP in this case, general purpose, costs us this much a month. The as is migration, if you just migrate everything to use hyperscale elastic pools, it's going to cost you slightly more. And again, your mileage may vary because there could be added costs for things like long-term retention backups. But then if you could optimize that setup by right sizing the compute and by leveraging newer hardware, and you may very well be able to save even further. I think hyperscale elastic pools is a game changer. It can be, if it's rightly used, and for the kinds of workloads that are best suited for hyperscale elastic pools, you can potentially not only have the efficiencies of sizing with the shared resource model, but affect your bottom line as well. Again, a big disclaimer on all this is costs are always subject to
Great.
your actual workloads. I just want to be truly transparent about that. But again, just trying to, kind of paint the picture of the possibilities.
Awesome. Great. Well, Arvind, that was a lot. I think folks learned a lot. I learned a lot. I'm sure our viewers learned a lot. Any final recap or notes before we close?
Thank you. So again, just to recap, we saw how hyperscale elastic pools use a shared resource model to deliver the convenience of sizing, and later we saw how it can potentially help us save costs. We looked at the inside elastic pool, view. We saw how though it has a shared resource model, we still ensure strong isolation between the workloads running in each of these databases. We showed you how to use the per database maximum to ensure that you can control and avoid contention between quote unquote noisy neighbor database workloads. And then we saw how quick it is and how predictable it is to scale Elastic Pool in Hyperscale up or down, or even things like adding replicas out or in, if you may. Finally, last but not the least, we just ended with that cost comparison and gave you an insight into potentially how hyperscale elastic pools can deliver further cost optimization. But again, just suffixing that with a little bit of caution on your mileage may vary as far as costs are concerned. With that, I just want to say thank you again for the opportunity to be on the show. For more details, I encourage you to go to our product documentation at Hyperscale Pools. And we are always willing and eager to listen to your feedback. You can either send feedback through the official feedback page, and here's an email alias that you can use to contact us if you have more direct and specific feedback for us to discuss. So once again, thank you so much for the opportunity, and looking forward to hear from you.
Awesome. Thanks, Arvind. Viewers, if you like this episode, go ahead, give it a like, leave us a comment, let us know what you think. We'll put some links in the description that Arvind shared to learn more. And we hope to see you next time on Data Exposed.